Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise ELE Electric Circuit Analysis paper solution series. In this tutorial, we are going to solve VTU CBCS scheme Electrical Circuit Analysis paper questions of Module 4 of syllabus 15E32. Friends, I prefer to emphasize on basic concepts, strategy and thinking process rather than detailed mathematical steps. I am sure you are well equipped with required mathematical skills. Hope you will enjoy the travel. Let's go ahead. Friends, first let us solve the question to find the Laplace transforms of the given functions. Consider the function sin omega t. Let Laplace transform of sin omega t is equal to f of s. Then, by definition, f of s is equal to integration 0 to infinity e to the power of minus st into sin omega t dt. But we know that sin omega t is equal to 1 upon 2j into bracket e to the power of j omega t minus e to the power of minus j omega t. By substituting for sin omega t, we get f of s is equal to 1 divided by 2j into integration 0 to infinity e to the power of minus st into bracket e to the power of j omega t minus e to the power of minus j omega t dt. By rearranging, we get f of s is equal to 1 upon 2j into integration 0 to infinity into bracket e to the power of minus s minus j omega into t minus e to the power of minus s plus j omega into t into dt. Friends, by integrating f of s, we get f of s is equal to 1 upon 2j into bracket e to the power of minus s minus j omega t divided by minus s minus j omega integration limits from 0 to infinity minus e to the power of minus s plus j omega t divided by minus s plus j omega limits from 0 to infinity. Note here we are using integration e to the power of minus at dt is equal to e to the power of minus at divided by minus a. By solving and rearranging, we get f of s is equal to omega divided by s square plus omega square. Therefore, Laplace transform of sin omega t is equal to omega divided by s square plus omega square. Friends, next we shall find the Laplace transform of cos omega t. We know by definition f of s is equal to integration 0 to infinity e to the power of minus st cos omega t dt. But cos omega t is equal to 1 by 2 into e to the power of j omega t plus e to the power of minus j omega t. By substituting for cos omega t, we get f of s is equal to 1 divided by 2 into integration 0 to infinity e to the power of minus st into e to the power of j omega t plus e to the power of minus j omega t dt. By rearranging and solving, we get f of s is equal to 1 divided by 2 into e to the power of minus s minus j omega t divided by minus s minus j omega limits from 0 to infinity plus e to the power of minus s plus j omega t divided by minus s plus j omega limits 0 to infinity. By putting the limits and solving, we get f of s is equal to s divided by s square plus omega square. Therefore, Laplace transform of cos omega t is equal to s divided by s square plus omega square. Friends, next we shall find the Laplace transform of the function t into e to the power of minus at. Note that this function is the product of two functions of t. The first function is t and the second function is e to the power of minus at. So, by definition, f of s is equal to integration 0 to infinity e to the power of minus st into t into e to the power of minus at dt. To solve this integration, we have to use the integration by parts. The rule states that let u be the first function, dv be the second function, then du is the differential of the first function and v is the integral of the second function. Then integration u into dv is equal to u into v minus integration v into du. That is, integration u into dv is equal to the first function into integral of the second function minus integration of integral of the second function into differential of the first function. So, using integration by parts, we get f of s is equal to t into integration 0 to infinity e to the power of minus s plus a t dt minus integration 0 to infinity of integral of e to the power of minus s plus a t dt into d by dt of t. By solving it, we get f of s is equal to 1 divided by s plus a square. Therefore, Laplace transform of t into e to the power of minus at is equal to 1 divided by s plus a square. Friends, next we shall solve second question. In this question, we are required to state and prove the initial value theorem. We know that initial value theorem helps to find the initial value of x of 0 of a function x of s directly using Laplace transforms. Initial value theorem states that x of 0 is equal to limit of s into x of s as s tends to infinity. Let's provide the proof. Friends, to prove the initial value theorem, let us use the operational transform of the first derivative, which states that Laplace transform of dx by dt is equal to s x of s minus x of 0. But we know that Laplace transform of dx by dt by definition is equal to 0 to infinity of dx by dt into e to the power of minus st dt. By equating the right hand sides of both the equations and applying limit as s tends to infinity, we get limit of s x of s minus x of 0 as s tends to infinity is equal to limit of integration 0 to infinity dx by dt into e to the power of minus st dt as s tends to infinity. But limit of integration 0 to infinity dx by dt into e to the power of minus st dt as s tends to infinity is equal to 0. Therefore, limit of s x of s minus x of 0 as s tends to infinity is also equal to 0, from which we get x of 0 is equal to limit of s x of s as s tends to infinity. Thus, the initial value theorem is proved. Friends, next we shall solve the third question to find the expression for I of t after the switch is closed at t is equal to 0 in the circuit shown in figure. It is also given that the initial charge on the capacitor before switching is 0. The strategy will be write the Kirchhoff's voltage equation for the circuit for t greater than 0, take its Laplace transform, then use the partial fraction expansions and get the equation in the standard form suitable to take the inverse Laplace transforms and obtain I of t. Observe that in the given problem, the applied voltage V is equal to 200 sin 500 t, which is sinusoidally varying function. We know that the Laplace transform of sin omega t is equal to omega divided by s square plus omega square. Here omega is equal to 500 radians per second. Therefore, the Laplace transform of the voltage function V of s is equal to 200 into omega divided by s square plus omega square. By substituting the value of omega is equal to 500, we get V of s is equal to 10 to the power of 5 divided by s square plus 500 square. Friends, observe the network after the switch is closed at t is equal to 0 as shown in figure. By writing the Kirchhoff's voltage equation for the circuit, we get R into I plus 1 upon C into integration I dt is equal to V. Let it be equation 1. By taking the Laplace transforms on both sides, we get R into I of s plus 1 upon C into I of s by s minus Vc0 divided by s equal to V of s. Let it be equation 2. Since the initial charge on the capacitor is 0, by substituting Vc0 is equal to 0, we get equation 2.1. Friends, by using simple algebra and solving and rearranging, we get I of s is equal to Vs divided by R into S divided by S plus 1 divided by RC. By substituting the values of A of s, R and C and solving, we get I of s is equal to 1000 s divided by s square plus 500 square into s plus 400. Now, let us use the partial fraction expansion. Let 1000 s divided by s square plus 500 square into s plus 400 is equal to a divided by s plus 400 plus bs plus c divided by s square plus 500 square. Friends, by taking LCM s plus 400 into s square plus 500 square and solving, we get 1000 s divided by s square plus 500 square into s plus 400 is equal to a plus b into s square plus 400b plus c into s plus a into 500 square plus c into 400 divided by the same denominator. By equating the coefficients of s square, we get a plus b is equal to 0, so a is equal to minus b. And equating the coefficients of s, we get 400b plus c is equal to 1000. By equating the constant terms and solving, we get minus 500 square into b plus 400c is equal to 0. By solving both simultaneous equations, we get a is equal to minus 0.976, b is equal to 0.976 and c is equal to 609.6. By substituting a, b and c in the equation of is and rearranging, we get is is equal to minus 0.976 divided by s plus 400 plus 0.976 into s divided by s square plus 500 square plus 609.6 divided by 500 into 500 divided by s square plus 500 square. By taking the inverse Laplace transforms, we get I of t is equal to minus 0.976 into e to the power of minus 400t plus 0.976 cos 500t plus 1.219 sin 500t amperes. Hope you have understood it. Friends, next we shall solve fourth question. This time to find the inverse Laplace transforms of the given functions. Before we find the inverse Laplace transforms, few points to remember are: 1. Generally, the given function f of s will be of the form of ratio of numerator polynomial say n of s and the denominator polynomial of say d of s. Number 2. The roots of the denominator polynomial could be real and distinct, complex and distinct, real and repeated, and complex and repeated. So, we need to observe the denominator polynomial and convert it to contain the appropriate roots using partial fraction expansion. Note it. First, consider the function f of s is equal to s square plus 5 divided by s into bracket s square plus 4s plus 4. This function as well could be written as f of s is equal to s square plus 5 divided by s into bracket s plus 2 whole square. So, now let us use the partial fraction expansion. Let s square plus 5 divided by s into bracket s plus 2 whole square is equal to a divided by s plus b divided by s plus 2 plus c divided by s plus 2 whole square. By taking LCM as s into bracket s plus 2 whole square and solving and equating the numerator polynomial on both sides, we get s square plus 5 is equal to a plus b into s square plus 4a plus 2b plus c into s plus 4a. By equating the coefficients of s square, s and constant terms and solving, we get a is equal to 1.25, b is equal to minus 0.25 and c is equal to minus 4.5. Using these values, we can write f of s is equal to 1.25 divided by s plus minus 0.25 divided by s plus 2 plus minus 4.5 divided by s plus 2 whole square. By taking the inverse Laplace transforms of f of s, we get f of t is equal to 1.25 minus 0.25 into e to the power of minus 2t minus 4.5 into t into e to the power of minus 2t. Friends, next we shall take up the second function. Let f of s is equal to 2s plus 6 divided by s square plus 6s plus 25. By rearranging the numerator and the denominator polynomials, we get f of s is equal to 2 into bracket s plus 3 divided by s plus 3 whole square plus 4 square. But f of t is equal to inverse Laplace transform of f of s. Hence, f of t is equal to L inverse 2 into bracket s plus 3 divided by s plus 3 square plus 4 square. This function f of t can be written as f of t is equal to 2 into L inverse s plus 3 divided by s plus 3 whole square plus 4 square. By taking the inverse Laplace transforms, we get f of t is equal to 2 into e to the power of minus 3t cos 4t. Friends, next we shall solve the problem to find initial and final values of the given functions using initial and final value theorems. Consider the function f of s is equal to s cube plus 7s square plus 5 divided by s into bracket s cube plus 3s square plus 4s plus 2. We know that f of 0 is equal to limit of s f of s as s tends to infinity. So, by multiplying the given function by s, we get f of 0 is equal to limit of s into bracket the function s cube plus 7s square plus 5 divided by s into bracket s cube plus 3s square plus 4s plus 2 as s tends to infinity. By solving and applying the limit as s tends to infinity, we get f of 0 is equal to 1. To get the final value, we know that f of infinity is equal to limit of s f of s as s tends to 0. By multiplying the given function f of s by s and solving after applying the limits as s tends to 0, we get f of infinity is equal to 5 divided by 2. It is so simple, isn't it? Friends, consider another function f of s is equal to s into s plus 4 into s plus 8 divided by s plus 1 into s plus 6. We know that f of 0 is equal to limit of s f of s as s tends to infinity. So, by multiplying the given function by s and applying limit as s tends to infinity, we get f of 0 is equal to infinity. Similarly, f of infinity is equal to limit of s f of s as s tends to 0. By multiplying the given function by s and applying the limit as s tends to 0, we get f of infinity is equal to 0. It is so simple, friends. Finally, we shall solve the sixth problem to find I of t in the circuit shown in figure by using Laplace transforms. It is given that the switch is closed at t is equal to 0 and all initial conditions are given as 0. This makes the problem more simpler. By writing the Kirchhoff's voltage equation for the circuit for time t greater than 0, we get R into I plus L into di by dt plus 1 upon C into integration I dt is equal to V. Let it be equation 1. By substituting the values of R is equal to 2 ohm, L is equal to 1 Henry and C is equal to 1 farad, we get equation 2. By taking the Laplace transforms on both sides and taking initial current through the inductance as 0 and initial charge on the capacitor as 0, we get 2I of s plus s I of s plus I of s by s is equal to 100 divided by s. Let it be equation 3. Friends, equation 3 is reproduced here for convenience. By rearranging using simple algebra, we get I of s is equal to 100 divided by s into bracket s divided by s square plus 2s plus 1. By simplifying and rearranging it, we get I of s is equal to 100 divided by s plus 1 whole square. By taking the inverse Laplace transforms, we get I of t is equal to 100 t into e to the power of minus t amperes. It is so simple, isn't it? Friends, I hope this tutorial has ignited some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.